Think back to grade school when you learned to multiply numbers on paper, rows of digits, partial products, and carrying columns. For small numbers, it feels routine. But here is the question computers face every second. What is the fastest possible way to multiply two numbers each with thousands of digits? Every time you make an online payment or send a secure message, your computer multiplies astronomically large numbers to protect your data. For decades, mathematicians believed the grade school method was essentially optimal, an unavoidable law of arithmetic. A 23-year-old graduate student proved them spectacularly wrong, and his insight still powers the software running on your device today. That algorithm is called Karatsuba multiplication. Before we can appreciate the breakthrough, we need a way to measure how fast algorithms are. Computer scientists use big O notation, which expresses how the number of operations grows with input size. If an algorithm does work proportional to n, the number of digits, it runs in O of n time, and its graph is a straight line. If work scales as n squared, we call that O of n squared, a parabola. For small inputs, the parabola may look harmless, but watch what happens as n climbs into the thousands. The parabola rockets upward, while the line stays nearly flat. Big O tells us which algorithm wins on truly large inputs, and as we will see, the grade school multiplication algorithm has a time complexity of O of n squared. Here is why grade school multiplication is O of n squared. Take a 3-digit number times a 3-digit number. Every digit of the bottom number must pair with every digit of the top number. 3 times 3 gives 9 individual single-digit multiplications plus carrying and adding. In general, for n-digit numbers, all n digits below must multiply all n digits above, giving roughly n squared operations in total. In 1960, the celebrated Soviet mathematician Andrei Kolmogorov stated at a Moscow seminar that no algorithm could beat this O of n squared bound. He believed it was a theoretical minimum, baked into the nature of multiplication itself. The room accepted it without debate. Kolmogorov went home convinced the question was settled forever. 1 week later, a student shook him to his core. Anatoly Karatsuba was 23 years old when he attended Kolmogorov's seminar. He refused to accept O of n squared as an immovable ceiling and set to work immediately. A week later, he had a proof. Kolmogorov was so astonished that he personally arranged the publication. The key idea is a split. Take x and y each with n digits, break each in half, write x as a times 10 to the half n plus b, where a holds the top half of the digits and b holds the bottom half. Write y similarly as c times 10 to the half n plus d. Expanding the product of x and y gives an expression with 4 smaller sub-multiplications: a times c, a times d, b times c, and b times d, each on numbers with roughly half the original digits. Expanding the full product gives 3 separate terms. First, ac times 10 to the n. Second, the quantity ad plus bc, that whole sum times 10 to the half n. And third, bd standing alone. 4 sub-multiplications, each operating on numbers half the size of the original. You might expect recursive splitting to fix everything, but it does not. Each level branches into 4 sub-problems, and the recursion tree grows until it reaches single-digit multiplications at the leaves. Analyzing the total work gives exactly n squared leaf operations, the same O of n squared complexity as before. The split alone gets us nowhere. But Karatsuba looked more carefully at those 4 sub-multiplications and noticed that 2 of them are redundant. The term AD plus BC can be computed without ever calculating AD and BC as separate steps. That single observation changes everything. The algebraic identity is this: a times d plus b times c equals the product of a plus b and c plus d minus a times c minus b times d. We already compute a times c and b times d for the other terms, so reusing them here costs nothing extra. That means the 3 distinct recursive multiplications are a times c, highlighted in red, b times d in green, and the product of a plus b with c plus d in purple. Every subproblem has half the digits of the original. The recursion tree now branches 3 ways at every level instead of 4. Summing the work over all levels is a geometric series, and when the algebra settles, we get O of n to the power of log base 2 of 3, approximately O of n to the 1.585. That is a provable improvement over O of n squared. The practical gap is enormous. For 1,000-digit numbers, O of n squared requires roughly 1 million operations, while Karatsuba needs only about 30,000. Python's built-in multiplication operator switches automatically to Karatsuba near 128 bits. That is precisely the crossover where the reduced exponent outweighs the overhead of the extra additions. Karatsuba's algorithm is now embedded in programming languages, cryptographic libraries, and arithmetic engines that power RSA encryption, secure web connections, and the matrix multiplications underlying modern artificial intelligence. The exponent on n, not even a rational number, emerges from the structure of a recursion tree. That is what makes this result so beautiful. A 23-year-old's algebraic insight scribbled in a week, still running silently on billions of devices.